model is this. A of t is the same with the same model with the compound interest that is compounded continuously. So A of t equals A0, the initial, original, or beginning, multiplied by e to kt. This is the exponential growth model. Normally, because it's exponential growth, k is a constant. It's the growth rate that is positive. Okay. What grows exponentially? Mice, birds, animals, bacteria, people. All these follow an exponential growth. They grow exponentially. Remember when the pandemic started, there were a few people who got sick, but then all of a sudden it exploded. Many millions got sick. This is an exponential growth model. It's terrible. And you probably heard people say, or scientists or medical personnel saying, we want to flatten the curve. We want to flatten the curve. We don't want this. People are dying. We want to flatten the curve. We don't want it to have such a growth. This is the fastest growing function, the exponential growth model. Okay. They said, okay, let's try and see if we can do this to stop all this increase that fast. Okay. Similarly to the exponential growth model, there is something called exponential decay. Okay, if mice, birds, grow exponentially, what decays? Radioactive substances. We hope we never ever get in touch with one. Radioactive substances. They decay. They don't grow. Their mass doesn't grow. Their mass diminishes. It's a decay. And what is the model? Okay, here's the model. We're going to use a different notation though. So this is the model. Identical. It's just that this k is a negative number. It's a constant. It's the exponential decay rate, and it will be a negative number. We don't like this notation for for the exponential decay. We prefer mass. M of t equals the initial e to kt. It doesn't matter. Would you have if you prefer this, use it. If you prefer this, use it. When you see mass, we really know it's exponential decay. If we see A, normally we think of the exponential growth, but it doesn't matter. As long as you know what you're doing, it's fine. Okay, now, one property of the radioactive substances is something called half-life. What does it mean? Let's suppose we have in this container, we have, 100 grams of some radioactive substance. If the half-life, H, let's say is 2 days, it means that 100 grams in 2 days will be 50. After 2 more days, it will be 25. After 2 more days, this will be 12.5, and so on and so forth. This is what the half-life represents. Some of them have a half-life of 5,000 years, if you can imagine. If I have 100 grams, I hope not ever, of such a radioactive substance, In 5,000 years, 100 grams will become 50. In 5,000 more, from 50 will drop down to 25. So they can have any sorts of half-lives. Okay, so I want to talk about this, and then we'll go backwards to 4.4. Okay, so here's the next problem. Use the exponential decay model, which is exactly the same. A0, e to kt. Just remember, k will be negative. To solve the exercise, the half-life of polonium-210, this is the name of the radioactive substance, is 140 days. So this is problem 87. A 140 days. Okay, fine. And of course, we have A of t equals A0 e to kt. Good. Now, how long will it take for a sample of this substance to decay to 20% of the original amount? How many days will it take for A0 to decrease or decay to 20% of A0? So this amount is the original. So I want 20% of A0. Okay, we're not there yet. So don't even look at the question. So we have that the half-life is 140 days. Okay, of any quantity. If it's 100 grams, then it will be 50 and 140. If it's 500 grams, it will be 250 in 140 days. Okay, so we are told that the half-life is 140, which means when t is 140 days, when the time is 140, A0 over 2 is the quantity that we get. I don't care for how much we started with. It's not even given to us. Any amount in 140 days, the resulting amount will be the original divided by 2. So this is another ordered pair. What ordered pair? 140 for t, A0 over 2 for A of t. So let's plug it in. A0 over 2 is A of t equals A0 e to k, which we do not have, times t, which is 140. So of 140, k. And you can say now you have two variables. Not at all. I simplify both sides by A0. So the left-hand side is 0.5. The right-hand side is e to 140k. Let's summarize this before we continue. We are told that the half-life is 140 days, which means when t is 140 days, the substance that we still have left is the original amount divided by 2. It's half-life. So when t is 140, this amount is A0 over 2. That's all I did. When t is 140, the current amount is A0 over 2. I changed 1 over 2 into 0.5. I copied e to 140k because nobody cares about the original amount. It's not even important. How do I solve this equation? As you see, the same over and over, the same steps. How do I solve this equation?
You will have to do the natural log on both sides.
Yes, excellent. We apply natural log to both sides. We have natural log of 0.5. Here I bring down 140k. I know the natural log is 1. I divide by 140, so k equals natural log 0.5 over 140. This is a formula if you want to memorize it as is. You don't have to do these steps, but the first time I really wanted to show you the steps. So what is this? So k is always natural log of 0.5 divided by the half-life. Again, what is k? K is the decay rate. Like we had the growth rate in the other model, this is the decay rate. Decay, or rate of decay. Okay, natural log is just a number. Natural log of 0.5, just a number. And h is the half-life. I prefer showing my students the steps so they don't have to memorize this formula. If you prefer memorizing this formula, memorize it. That's fine. Good. So I have to divide k. So the numerator is always natural log of 0.5, and the denominator is always the half-life to determine the rate of decay. So I plug it in. And let's see what we get. So we have natural log 0.5, and we divide by 140. And we prefer 4 decimal digits. As expected, it's a radioactive decay. K is a negative number, negative 0.00. I have 4, 9, and 5. So I have to change the 9 into 0 and the 4 into 5. So it will be just this, negative 0.005. Good. Now I put it back in the model as we just did on the exponential growth. As you see, this is absolutely the same. It's the same model. The steps are the same. It's just the only difference is here. There is nothing else. And of course, now we know what the half-life is and the formula for the rate of decay. That's it. The models are the same. So then A of t equals whatever the initial is, which we don't care, e to negative 0.005 t. We found the model. Now, so A0, in other words, A of t, decreases to 20% of A0. So maybe I should just say here just A, not A0. So A decrease to 20% of A0. So when we say 20% of A0, what do we really mean? Which operation? 20% of A0. If I tell you I have in my pocket 10% of what the amount you have in yours, what does it mean? What operation is that? Let's say you have $100 in your pocket, and I'm telling you, in my own pocket, in my pocketbook, I have 10% of what you have. What operation is that?
Would it be multiplication?
Of course. Thank you so much. The word of means multiplication. So 0.1, which is 10%, multiplied by 100. Correct. Good. So now we come back. They say 20% of A0. 20% of A0 is this quantity. So how long it would take for the amount we have on the table to be 20% of A0? But this means exactly what Christy said. 0.2 A0 equals A0 e to negative 0.005 t. Exactly. That's what it means. Exactly as we had with the previous situation in which it was half of A0. Now it's less than half. It's 0.2 of A0. Of course, we don't care about A0. We're going to divide both sides by A0. So then we have 0.2 equals e to negative 0.005t, and the fourth time, the same theme in 20 minutes. What do I mean by that? This, and where was it? This was the first time, this was the second time, this was the third time, all of them the same equation, all of them, and this is the fourth time. So you should be dreaming about this equation. Again, natural log, natural log 0.2 equals negative 0.005t. So then t is natural log 0.2 negative 0.005. Make sure t is never negative, right? So careful. You have to put parentheses around the denominator because it's a negative number, so you incorporate that. So the numerator is natural log of 0.2. And we divide in parentheses, negative, we start with this negative, 0.05. No, 0.5, and close. Okay, so we need the time in which it goes from 100% to 20%. It definitely has to be more than 140 days. It must be, because it gets to 50%, down from 100 to 50% in 140 days. From 100% to 20%, it has to be more than 140 days. Here it is, roughly 322 days. So t approximately 332 days. So if I have 100 milligrams, it gets to 20 milligrams from 100 to 20 in 332 days. But it gets from 100 to 50 grams in 140 days. Confirm based on what we have as the half-life, which is 140. Any questions on this model? Oops, I have to keep my mouth shut for 10 minutes. Yes, 10 minutes, sorry. I'll keep my mouth shut, promise.